In the next part of this presentation, I'm going to introduce examples of calculating equilibrium. And in the part one of this, we calculated the equilibrium constant itself, and then I added in a reactant or product to show what happens to the value of the reaction quotient when I have non-equilibrium. Now we're going to suppose I start with a non-equilibrium. We want to continue that problem. Start with a non-equilibrium situation and calculate explicitly what the concentrations are when we finally do get to equilibrium. So the example that we're going to do is this one. Bromine reacts with chlorine to produce BrCl. The reaction, the equilibrium constant is given. We're given that to start. It's 7, so we're not going to calculate that. That's just given. The initial concentrations are given here. Bromine is 0.1, chlorine is 0.15, and BrCl is 0.1. Well, the first thing I'm going to do is calculate what is the value of Q. If for no other reason than if Q happens to be equal to K, then we're done. We don't have anything more to calculate. But also to see which direction the reaction is going to move. So putting in the values for 0.1 for bromine chloride and raised to the second power, 0.1 for bromine, and 0.15 for chlorine. Carrying out the calculation, I see that Q equals 0.667. Since this number is less than 7, the reaction is going to move to the right. And so now the question is, how far to the right is it going to move, and what are the concentrations at equilibrium? To do this, first I define an unknown extent of reaction X. That is, X represents to what extent in moles per liter does the reaction move forward. And we're going to construct something, a table, an IC Etable. And this table is a convenient means for showing what happens during a reaction. I stands for initial, C stands for change, and E stands for equilibrium. Across the top, I'm going to have labels representing the reactants and products in the reaction, bromine, chlorine, and BrCl. Initially, these are the concentrations that I had at the beginning, 0.1, 0.15, and 0.1. Now, if the reaction moves forward by X moles per liter, well, the change, since the reaction is moving forward, bromine is going to decrease by X, by my unknown X. The stoichiometry of the equation tells me that chlorine will decrease by exactly the same amount because bromine and chlorine react 1 to 1. On the right-hand side, so remember that the reaction goes from here to here. And also remember that BrCl, 2 moles of that are produced for each mole of bromine or chlorine that is reacted. And therefore, BrCl is going to increase by twice X, again because of the stoichiometry of the equation. Now I simply add the numbers from the initial to the change to get my equilibrium concentrations, 0.1 minus X, 0.15 minus X, 0.1 plus, and this should read, this is a mistake, this should read 2X, 0.1 plus 2X. Okay. So I insert these into the equilibrium expression, so products on top, the bromine BrCl on top, the 2, the raised to the power of 2 because of the coefficient in the reaction, and the denominator, the equilibrium concentrations of bromine and chlorine. And now all I have to do is solve that equation for X. Now this is the most complex problem that we're going to introduce, because this involves a quadratic. And there are lots of opportunities. You can solve it, but there are lots of opportunities for making mistakes. So we're just going to plow right through it and see how it's done. We expand the numerator and the denominator, expanding the squares. So when I do that, I get these values for the numerator, 0.01 plus 0.4x plus 4x squared, and this value for the denominator. Now, what I want to do is put this into a quadratic form, get everything into the numerator. So if I multiply the numerator and denominator, I multiply both sides of the equation by this denominator. So multiply both sides by that. So this the 7 will become 7 times this quantity. Just for convenience, yes. Okay. Yep. This is a result of multiplying this denominator by 7. I carry that out, and now I want to bring everything over to one side of the equation in order that I can get it into a standard quadratic form. So, for instance, I will subtract 4x squared from 7x squared to get 3x squared, and so forth. I'll do that to each term, and I will end up with, and I just rewrite it in this order. So the x term comes from 1.75x minus 0.4, that's minus 0.215x. And the constant term comes from 0.105 minus 0.01, and that's 0.095. Now it's in our familiar standard quadratic form, ax squared plus bx plus c equals 0, with a equal to 3, b equal to minus 2.15, and c equal to 0.095. And you may recall, this is the quadratic formula. So when I write in standard quadratic form, x has two solutions given by the plus and minus signs here. Putting those numbers in, I get the two values are x is 6.7, or x equals 0.0473. If you recall before that the bromine, for example, in the equation was 0.1 minus x. If the bromine is 0.1 minus x, notice that x cannot possibly be 0.670, because that would give me a value of a bromine less than 0, a negative value, and concentrations can't be negative. And when we do an equilibrium problem where it comes out to be a quadratic, it's always true that one of the solutions doesn't make any sense and can be discarded. So therefore, this must be the solution. X is 0.0473. So as I stated, the first solution is impossible. So now I go back to that same IC Etable, and now that I know the value, I put that in. So here's the first line, and in this next line, instead of the minus x 2x, I put in the values of x that I received, that I got, which was, so minus x is minus 0.0473, and plus 2x is plus 0.0946. Adding these together, I get these three numbers, and these are the three equilibrium concentrations. Bromine is 0.0527, chlorine is 0.1027, and BrCl is 0.1946, as stated here. Since when I'm doing a problem like this, as you can see, there are many opportunities for making mistakes. I like to substitute everything back into the expression for the equilibrium constant to see if it makes sense, if I do get the equilibrium constant. So the value of Q, the reaction quotient that I have for these concentrations, I put in the BrCl, bromine, and chlorine, and carry out the calculation. I get 6.997, and if I round properly, this should actually be 7.00, which is the original given value of the equilibrium constant. So my solution checks out, and these would be the values of the reactants and products at equilibrium.